So, good evening, good afternoon, good morning, wherever you are. It's my absolute pleasure to introduce and welcome my old friend, Gleb Kakazei, from University of Porto in Portugal. Very eminent scientist in the field of nanomagnetism and now in spintronics and also spin wave spectroscopy in particular. And it is the 95th webinar of this webinar series, which we started about 2 years ago in 2020, just during the lockdown, during the pandemic. And I'm very happy to see that this series is still continuing only because of speakers like Gleb and the audience like you people who are there with us today. So on behalf of my team, Braj, Puspendra, Shakti, Swayam, Kitiz, Ajar, and others, I like to thank you, Gleb, for accepting our kind invitation and joining and taking the trouble to give a lecture. So Professor Kakazei is really a well-known name in the field of nanomagnetism, spintronics, spin wave spectroscopy, magnonics, and so on. Nevertheless, I like to give a very brief introduction about him, just for the benefit of a few students. So Gleb actually graduated from radio physics department of Kiev National University in Ukraine in 1989, and he obtained his PhD in physics from Institute for Metal Physics, National Academy of Sciences of Ukraine, that is NAZU, in 1996, and joined Institute of Magnetism in NAZU as a staff scientist. He was a postdoctoral researcher at Institute for Materials Physics of University of Porto in Portugal from 1998 to 2001, and at Ohio State University, Columbus, US, in the period 2001 to 2004. In 2004, he returned to Institute for Magnetism, that's NAZU, as a senior research scientist, and in 2005 on a Doctor of Science degree, that is the habilitation, equivalent to the other European countries. In 2006 till 2007, he was on sabbatical leave at Institute of Material Sciences of Madrid in Spain. And in 2008, he was employed by the FEBID as a scientist at Porto in Portugal. And in 2014, he was promoted to principal scientist and became a group leader subsequently. In 2013 and 2014, he had a 1-year stay at National University of Singapore in the group of Professor Ade. I just realized that he had joined. Thanks, Ade, for joining. His research activity focuses on magnetization dynamics in magnetic nanostructures, development and advanced characterization of different magnonic and spintronic devices, and design of new types of skyrmionic and vortex systems. He has got numerous awards, just to tell, let's say, 2 of it. He has got the grant of the President of Ukraine for outstanding achievements in science in 2010, and Lev Subnikov Prize by the National Academy of Sciences of Ukraine in 2013. So with this brief introduction, I again welcome you, Gleb, and all of you to this webinar. Just a short announcement that during the lecture, we don't take any questions. If you have any questions, you can kindly write that in the chat box or raise hand. After the end of the lecture, first we will take a group photo. So I would request Gleb to, stop sharing for 1 minute. Yeah. And I would request all of you to switch on your camera, and we will take a group picture for our souvenir later on. And then we'll come back to the question answer session, and Gleb can again share his screen. Okay, so with all this, it's absolutely now the stage is set for your talk, Gleb, and looking forward to a lecture. Thank you very much.
Okay, thank you very much for such a nice introduction. And today I will speak about, the area that, in fact, I was developing for my whole research career, because my master thesis was also about ferromagnetic resonance in some EEG films. And I think over the years, with all the development in nanofabrication, in detection techniques, so finally we arrived to the situation when it is possible to study by a technique that was initially considered as a macroscopic technique, individual elements, and just not detect signals from them, but detect small spin wave excitations from these objects. And this helps a lot in the characterization of elements that can exist only in such a in very small quantities. So I will start from the brief introduction of ferromagnetic resonance technique and spin waves. I will speak about basics, experimental methods, and then I will switch to our recent results. There was considered propagating spin wave, like a spin wave inverter on single nano defect, and as well as detection of standing spin waves in individual elements and demonstration of control of the properties of these elements. And finally, I will briefly introduce nanovolcanoes, some really 3D nano element, and will show that its properties cannot be considered like a sum of properties of the sub-elements it consists from. So let's start from the introduction, ferromagnetic resonance. And so this effect was discovered in the late 40s. And what was found is that if the magnetic ferromagnetic sample is placed into the combination of two magnetic fields, one continuous magnetic field in principle used to saturate the magnetic element, and another one is a radio frequency field of a much smaller amplitude, but in frequency typically in gigahertz range. At some combination of DC and AC fields, the sample will start to absorb microwave energy, and this will lead to the precession of magnetization vector. And optimal configuration is when the angle between these two fields is orthogonal. And this precession of magnetization vector around the direction of external magnetic field called the Larmor precession. So this is a relatively simple equation, and the way to observe this effect was you can sweep either the amplitude of DC field or you can sweep the frequency of AC field. And of course, initially people were using the sweep of DC field. So this is a demonstration. You are sweeping the DC field, and at some moment when the resonance conditions are met, you have a large precession of magnetization vector, and you have an absorption of radio frequency field. So, and what is very important about ferromagnetic resonance and why it is such a useful method for determination of magnetic properties like saturation magnetization? It is because in this Larmor in the initial equation, instead of external field, internal magnetic field is used. And this means that you can already use the shape of the sample to produce a large internal field. And concept of ferromagnetic resonance was developed by famous theoretician Charles Kittel. And he introduced the term of the magnetizing field. And the easiest way to introduce the magnetizing field is ellipsoid, because in case of ellipsoid, you don't have stray fields around this figure. And So any ellipsoid can be characterized by 3 demagnetizing field. And in Kittel theory, this 3 demagnetizing factor can be normalized as a sum of 3 of them, either 1 in international system or for pi in SGS system that is, well, typically people in area of magnetism were using it at least at this time. And so in case of, well, globe, so all the demagnetizing factors are equal to 1/3. And typically, if you will apply field in different direction, nothing will happen with ferromagnetic resonance signal. It will always appear in the same place. However, if you will switch to like object like thin disk, in this case, there will be, if the external field applied in the film plane, typically internal field will be equal to 0, and the signal will appear in low external field. However, if you will apply your external field along the normal to this disk, in this case, you will have a lot of stray field around, so internal field would be huge, and this will lead to the appearance of the signal in the much higher external fields. Similar situation will happen with another object with axial symmetry rod. Well, of course, in this case, easy and hard direction will change. So the basic idea of ferromagnetic resonance is you are applying your external field in different direction along the film plane, perpendicular to film plane at arbitrary angle between these two directions, and you obtaining some kind of angular dependence of ferromagnetic resonance signal. And by using very simple theory, you can easily extract from this angular dependence saturation magnetization and also gyroscopic factor. In case of gyroscopic factor, this is a less interesting parameter, but still it gives some information about the sample. For insulator, it always equal to 2. In case of metals, it varies from 2 to 2.2. However, the main parameter that we are interested in when we are studying the sample is saturation magnetization. Of course, all I'm saying is correct only for the case when film is relatively thick. So I would say above 3-4 nanometers. And in this case, surface energy is not playing significant role. Because main advantage of ferromagnetic resonance, you can extract magnetization without knowing the exact amount of material. You just need to know the shape of the element. But the main disadvantage is you cannot separate saturation magnetization and perpendicular anisotropy. And in case you have really complicated, like multilayered structure, ferromagnetic material, noble material, to separate, you need a combination of ferromagnetic resonance spectroscopy and magnetometry to determine both of these values. So that's pointed. So this is the formula. And so this is just some simple example from 50s, how people determined the saturation magnetization of cobalt film. You can see it's quite close to the values of bulk cobalt. It is 138 versus 1.42 for bulk material. So everyone was happy in the 50s, 60s, but let's see how we can measure ferromagnetic resonance in the most convenient way. So it all started with resonance cavity technique. So first you need to have a generator. Then generator, of course, should be very monochromal, and typically at this time klystron generators were used for these purposes, and klystron generators were main components of different radar military systems. And from that time, in ferromagnetic resonance spectroscopy, we have terms of X-band, K-band, and Q-band. These are terms that were used by US military to determine frequency range. So in military, it was please switch from X-band to K-band, and the operator knew that he needs to switch between these frequency ranges. And so the signal, microwave signal generated by klystron goes through the waveguide to the cavity. Then in cavity, it interacts with material, and you see that cavity is placed into between the poles of electromagnet. So you can already sweep the external field easily using many standard. And then it returns by waveguide to the detector. And microwave detector, well, nowadays people mostly using different semiconductor detectors that change the voltage depending on the microwave power. So very simple scheme. You just need 3 components. Of course, in reality, it is a bit more complicated. And so this is a typical design of universal X-band resonator. And I would like to say that people prefer X-band because in this case, the wavelength is 3 centimeters. So the typical size of the sample under study can be around 3-5 millimeters. So it's quite easy to handle a sample of this size, and it can be placed into the resonator. And optimal place for the sample is in the center of the resonance cavity, and you can excite different standing electromagnetic waves inside, but so-called TE102 is the most efficient for ferromagnetic resonance. And if you will place the sample using some kind of computer-controlled goniometer, you can easily rotate it inside the resonator, so very quickly you can measure angular dependence from in plane to out of plane. And what is additional advantage of using such a cavity technique is that you can additionally modulate the external field by low frequency modulation coils. I mentioned that ferromagnetic resonance appear in the gigahertz range. So if you will modulate the external field in kilohertz range, what you can do, you can use so-called derivative detection. So this is a normal absorption line of ferromagnetic resonance, but if you will modulate external field, you will observe the derivative of your resonance signal. And this really improves the sensitivity hundreds times. And also you can immediately determine the central position of the line as well as line width. So this technique was found to be very useful, but of course it leads to the more complicated construction. You need to introduce lock-in amplifier. And so this is a more realistic scheme of modern day cavity-based ferromagnetic resonance spectrometer. And in some way, we are lucky that also, well, the ferromagnetic resonance effect is similar to electron paramagnetic resonance effect used by actively in chemistry and in biology. So the same device, spin electron resonance spectrometer can be used for all for different applications. In case of our center, we are sharing our cavity-based spectrometer with people from chemistry and biology. And of course, commercially, well, Bruker fabricated thousands of these devices, and electronics is really polished. And the advantage, high speed of sweeping, you can just 1 minute per spectrum, very high resolution, because position of the signal can be determined with accuracy of just few Ørsted. And by using a computer-controlled galvanometer, you can easily obtain any configuration and study angular dependence of ferromagnetic resonance. So just need 10 minutes to measure the whole spectra. And of course, it comes at some kind of disadvantage. Frequency is fixed, and frequency is fixed by the size of cavity. Of course, well, there were attempts to manufacture a cavity with a moving wall, but this all leads to decrease of sensitivity. And well, because of this fixed frequency, it is also impossible to study materials in the absence of magnetic field. As we know now, there is a lot of different magnetic structures like vortices, fermions that exist in the absence of magnetic field. And people are also very interested in their dynamics. But unfortunately, the dynamics cannot be studied with this cavity-based ferromagnetic resonance spectrometer. And well, maybe I will, okay. I already mentioned that ferromagnetic resonance is uniform precession of magnetic moments in the whole samples, is a very useful technique to study saturation magnetization of the samples, but this is not the only possible configuration of excitation, excitation of magnetic dynamics. Another possibility of excitations are so-called spin waves. And there are two types of spin waves: traveling spin waves and standing spin waves. And in case of, well, I will speak about traveling spin waves later, but what is interesting also for cavity-based ferromagnetic resonance is standing spin waves. And in case of standing spin waves, what happens for some reason, because you are studying the sample with restricted geometry, you have pinning of magnetic moments at the edges. In the simplest case, thin film, you have pinning of magnetic moments at the bottom and top surface of magnetic field. And so you have a precession with the same frequency, but with different amplitude in the different areas of the sample. And so this is an example of ferromagnetic thin film. Well, uniform precession, everything is clear. In case of standing spin waves, you have lower standing spin wave mode pinning at the edges, maximum in the center. Next mode, pinning at the edges, maximum at some thickness, zero excitation in the center. And so and we have modes with higher and higher numbers. And what is also useful about these standing spin waves is by measuring this spin wave resonance, you can immediately obtain another important parameter, is so-called exchange stiffness constant. Its correspond is to how closely interacting neighbor magnetic moments in ferromagnetic material. And this parameter is, well, there are only few methods to study it, and this is perhaps one of the easiest. So of course, the higher the mode number, the lower the amplitude. And basically the peculiarity of ferromagnetic resonance is that you cannot measure actually the even modes, because for even modes, the net magnetic moment of this mode is equal to 0, and because of this, the modes with number 2, 4, 6 are not coupled with RF field. So you can see only odd modes, and this is just some again example from 60s, because theory of standing spin waves were developed again by Charles Kittel in 59, and in 1 year these spin waves were already discovered by experimentalists. So these are figures from this paper. And but let's switch to nanoelements, because within the last 20 years, the development of different lithographic technique allow it to fabricate nanoelements with smaller and smaller sizes. And when I was a postdoc at Ohio State University, we used this ferromagnetic resonance spectrometer to study spectra of perpendicularly magnetized array of circular disks. And of course, in this case, we had millions of, well, around few million of disks. And what we found a very pronounced standing spin wave resonance in perpendicularly magnetized dots. And we collaborated with theoreticians Andrei Slavin and Konstantin Guslyenko, who wrote a theory that allowed to, let's say, explain our observed dependence with very high accuracy. What they considered that standing spin waves are zero-order Bessel functions. And in fact, it's interesting that if we will excite standing waves in a macroscopic musical instrument like drum, so by using sticks, you will observe similar modes. So these modes were called drum modes. And you see the profiles are, well, relatively simple, very well described by Bessel functions. Also, what was taken into account that the magnetizing factor was calculated for each separate mode. And just a few simple precautions allowed to describe standing spin waves with high accuracy. And what it means that just fabricating elements in the, of course, perfectly like perfect circles, and applying the field perpendicular to the plane and measuring this spin wave resonance, you can immediately obtain the saturation magnetization and exchange stiffness constant. But okay, so this was our macroscopic work on macroscopic elements. And I already mentioned that in many cases, we need to study films in unsaturated state. And the cavity approach is not working in this case. And for these purposes, what people are using, they're using different broadband systems, and the typical broadband ferromagnetic resonance system is based on coplanar waveguide, and in coplanar waveguide, so it consists of signal line and two ground lines, and you can also excite radio frequency fields in the same range, but here you're not limited by the size of the resonator. You can excite these frequencies from megahertz to tens and even hundreds of gigahertz. And as a source and as a detector, typically people are using vector network analyzer. Vector network analyzer allows to generate frequencies in this whole range, and it also includes detector that, in addition to phase amplitude, can detect the phase of the propagating wave. Of course, I already spoke that in case of cavity, you can place the sample into the center of the cavity, so it's just in the maximum of microwave field, and the quality factor is very high of this. In case of coplanar, you need really to take a precaution to fabricate samples. The simplest way is to place the macroscopic sample on top of the coplanar, but it will lead to quite non-uniform RF fields in different areas. Therefore, the optimal way is to fabricate samples just on top of your signal line. In this case, really, you have a very nice signal-to-noise ratio. And this image is from the paper of Novosad and Bader in 2005. So when I arrived to University of Porto, so we had some, of course, VNA, and also all the power, magnet and power supplied from Bruker. So we just started in a classical way. Just place it waveguide VNA on top of our magnet, and what we found is that in this configuration, VNA still can feel the stray fields from the magnet, and this disturbs its operation. So we already switched to the configuration where the VNA placed far away from external magnet. So of course we obtained a new power supply that can sweep fields from +15 to -15 kilohertz, and also, we developed a so-called picoprobe technique that allows us to measure nanofabricated samples, as well as also by using antennas for emission and detectors to study traveling spin waves in our system. And so we started our experiments with propagating spin waves. So we entered the area of magnonics, and so it was, well, magnonic crystals were developed in the last 20 years, and initially they were designed as some kind of filters of frequency filters, because idea of magnonic crystal is similar to the idea of photonic crystal, that waves of some lengths can propagate through the signal, through the system, and some cannot. Well, and this determined by the geometrical dimensions of magnonic crystals. So in case of magnonic crystal, you need to periodically change one of the parameters. It may be magnetization, thickness of magnonic, well, like in this case. And so the options are quite, well, I would say limitless. And but what we wanted to see is, can we create such an important element of spin wave logic as a signal inverter? And you know now that spin wave logics is a really very popular direction, and some people consider that it can be used in the next generation of computers. But for this, you need to know how to manipulate the signal. And the simplest element is so-called XNOR gate, and it can be, well, demonstrated here. Initial work on this element was performed by Hillebrand's group in 2008. And the idea is simple. If both signals are in phase, then you have a large signal on the output, so signals are summed, and you have one at the output. And in case if two signals have different phase, they will be subtracted, and you will have 0 at the output. And one of the designs of such phase shifter was proposed by Dirk Grundler group in 2018. So they were used array of dipolar coupled nanowires, and one of the wires had different lengths. As a result, it was possible to magnetize it separately from other wires, and as a result, you had a magnetic defect in the center of magnonic crystal. And they demonstrated that it's possible by manipulating with the central element and manipulating by external field and frequency. It is possible to shift the propagating phase by like 120, 150 degrees. They still were not able to achieve the complete phase shift. And in our experiment, we joined forces with group of Professor Michael Huth from University of Frankfurt, who is a well-known specialist in so-called FEBID technique. And FEBID deposition is some kind of combination of classical lithography and deposition. And so idea is you are introducing into the system the gas that consists of magnetic elements and organics. And then you are exciting the substrate by means of focused electron beam. And in the area where the substrate is excited by the beam, we have a deposition of ferromagnetic material, and all these organic components are going outside. And therefore, by using this technique, you can easily create structures of different shape. And we created a waveguide made of cobalt-free iron, and then we introduced a defect in the center of this waveguide by ion irradiation. And what we found is that with this groove, when the groove is quite deep at some particular fields, it was possible to completely shift the phase of propagating spin wave by 180 degrees in comparison with the just continuous waveguide. So if we will place in parallel reference waveguide and groove, we will have a mixture of two signals with opposite phase and the realization of spin wave logic. What we studied this effect because simple simulation demonstrated that just existence of the groove cannot lead to full rotation of the phase. And we found that the full inversion of the phase happens because of the combination of existence of the physical groove and change of magnetization under the groove, which means that with proper design, one do not need the groove to create a phase shifter. It's just necessary to change magnetization in the area by proper value. So this was our first experiment on individual element, and just to show that we really were able with our relatively simple setup to detect the element with size 1 micron by 2.5 microns. And the question was, can we do the same with individual disks? Remember our work on standing spin waves in arrays of disks? So can it be done for this individual disk? So this is just intermediate summary that says that we created a new design of spin wave phase inverter, and it can be easily on chip integrated. So, but what about the detection of the signal from a disk of smaller size? Can we do it? And what appears is, yes, we can. Again, we used FEBID technique to fabricate individual disks of different size. You can see the smallest size of the disk was 200 nanometers. And we designed it, of course, in this case, we use not just one place samples on coplanar, we place sample on individual substrate, and then we fabricated coplanar with a very narrow central part and on a separate substrate, and we just moved one of the substrate over another substrate. So in this case, we can have only one element under the waveguide. Sample is very close to waveguide, so the coupling is perfect. And let's see what signals we can read from such a small elements. And of course, again, we used perpendicular geometry. So just to excite this drum modes with the profiles of Bessel functions of zero order. And what you can see, well, diameter 2 micron, perfect signal. Diameter 1 micron, still perfect signal, although we see some kind of noise. Let me see if, oops, okay, perhaps. And still we were able to decrease our signal. I'm just trying to find strange. Perhaps I don't have it. But we were able to read the signal from elements as small as a radio of only 100 nanometers. Of course, in this case, there were only few signals. And the important comment, we fixed the thickness of the dots to 40 nanometers to in some way to mimic our experiments on array of disks. And because of this, for really small diameters, instead of flat disk, we had really some kind of 3D object. So it definitely affected also the excitation of standing spin waves in such a system. However, what we found? We found that theory developed by Guslienko and Slavin for flat disks still very capable of describing the properties of this, well, almost 3D disks. It's still the same spectra. And you see theory is perfectly describing all the peaks inside each spectra. But what was a bit surprising result for us, what we found is that magnetization of our individual elements fabricated by FEBID technique depends on the diameter. So it means that on the contrary from classical deposition schemes, magnetization of the sample depends on the regime of fabrication regime, because the smaller elements, the less time you're using to write these elements using focused electron beam. So what we decided to check is what will happen if we will write one monolayer of atoms, then park the beam for some time, and then repeat the fabrication of next level. And what appears is, depending on this parking time, we can significantly vary the magnetic properties of these FEBID fabricated disks. And additionally, of course, we can change their properties also by using ion irradiation by gallium. Of course, this gallium radiation is used to decrease the magnetization, but this parking time is used to increase the magnetization. Because the more time we used between the fabrication of individual monolayers, the higher magnetization was obtained. And the conclusion was that, there is a limited amount of gas in the chamber. If we are writing our elements too quickly, so we are using all of the gas, and as a result, instead of high quality ferromagnetic materials, we have a lot of organic component in our disks, which is of course not good for the fabrication. So what we were able to demonstrate that combining this parking time and gallium irradiation, we can fabricate elements with magnetization varying from 720 mu per cubic centimeter up to 1,400. So just by playing with these parameters, we can create material with the properties either of permalloy or cobalt. And it also means that we can create magnonic crystal where the magnetization is varied in the broad range. And another interesting experiment was to check how accurate is this theory. So we measured films, fitted them using analytical theory, extracted saturation magnetization and exchange stiffness constant, and then used these two parameters in micromagnetic simulations to reproduce the spectra. And what you can see is really amazing correlation between these two simulations, experiment, and analytical theory. So it means analytical theory works perfectly in the whole range of aspect ratios. And finally, last sample I want to discuss is so-called nanovolcano. Again, same FEBID technique, and this sample is a combination of disk with a ring on top of it. External diameter of the ring corresponds to diameter of the disk, and you can vary the internal diameter. And again, by the developed technique, we can study individual elements and applying external field perpendicular to the axis. We can excite different standing spin waves, and let's see how they're different from the standing spin waves in disk. Of course, here well, first you can see that it can be considered either as a large disk with a large ring with a disk inside the ring, or just a combination of disk and ring of the same diameter. Of course, the reality appeared to be much more complicated. You see here the internal fields inside this nanovolcano, and of course the existence of this crown significantly change internal field inside the disk, and it has nothing in similar with a separate disk or ring. We still observed two, let's say, type of signals, and we call them disk modes and ring modes, but this modes has nothing to do with modes of individual elements. Here you can see internal fields, well, standing spin waves inside this volcano, and comparison with the spin wave modes in just a simple disk. And what we can say immediately that the lowest modes similar to the lower modes of the disk. However, because of this crown and because of stray fields generated by crowns, these modes are more focused in the center of our element. And of course, higher order modes are excited already in the whole element. So they're excited both in the center and at the edges of the disk. So an interesting combination. In fact, we were just playing with the shape. However, you see that processes in some way similar to processes in disk, but there is additional degree of freedom. How these structures can be useful for practical applications? First of all, extension of 2D nanodisk into the third dimension. So in this case means that the appearance of ring on top of it allows one to engineer lowest Asian frequencies by using samples with 30% smaller footprints. So you are increasing the thickness, and in this way you can obtain the same properties in the smaller elements. And additionally, varying the crater diameter by quite small numbers, we can significantly change higher order modes. So you see lowest mode are not depending on the crater diameter, but higher order modes can be tuned in a quite broad range of several gigahertz just by varying the crater by 20 nanometers. So it's again a nice well, demonstration of what can be done, improved with creating of nanoelements with a real 3D shape. And well, I think I already described these conclusions, and I'm arriving to the end of my talk. What I really want to acknowledge is significant contribution of my colleagues. My senior scientist, Dr. Sergei Bunyaev, Alexander Dobrovolsky, and Andrei Chumak. In the beginning of this work, Alexander Dobrovolsky was working with Mikhail Huth. Now he is actively working with Andrei Chumak at University of Vienna. Of course, Professor Mikhail Huth, who provided all these very nice samples. And we continue our collaboration with Konstantin Guslyenko, who is one of the lead theoreticians in the area of magnetization dynamics. And so we already here demonstrated that his old theory is still working with modern thick elements, and now we are developing theory for different types of vortices and skir muons. And thank you for your attention.
Yeah, thank you very much, Gleb, for this wonderful overview. And actually, I really like to appreciate and express my thanks for giving a very good amount of introduction in the beginning for the beginners. We have a lot of students in the audience. I'm sure they would definitely appreciate that. So thank you very much for your very nice lecture. On behalf of everyone, I clap that. I would like to request you to stop sharing, and I would like to request all of you to switch on your camera for 30 seconds. And let's take some picture, group photo. Thank you, Rana. So please, please turn on your camera. I hope you can do that. Yes, so many have done it. Puspendra, you may take. Hi Dale, good to see you.
Yes, I am taking the photos.
Okay. Oh, hello, hello.
Just say smile.
Smile. Yes, sir, I have taken photos.
Okay. There are two screenshots you need to do. Okay. Just, all right. Very well. I'd like to request you all to turn off your camera. And Gleb, you kindly share again your screen.
Okay, I will.
In chat box, there are two questions. I will read it for you, or you can also read. You can.
Let me see where. Okay, I think here it is. Sure.
So,
okay. Yeah, I think I can see the questions. Yeah.
So the first question is, Professor, could you please explain what exactly happens to the electronic states in the ferromagnetic resonance conditions? I mean a transition from one spin state, say up state to down, or something else.
I would say that, well, there are different theories, but let's say the macroscopic theory shows that there are no two well-determined electronic states, like in case of electron paramagnetic resonance, where you are just exciting upper level, and then you see a relaxation to another. You can consider this as a macroscopic system. So you deal with macroscopic vector. It can be, in fact, inclined from external direction by direction of external field by any angle. Still, this in most cases, this precession will happen in exactly the same way. Why we need our microwave field, microwave power to support this process is because if there is no microwave power, so for example, you applying pulse, you are removing, you inclining magnetic moment from direction of DC field, so the precession will take place very shortly, like tenths of nanoseconds. And in fact, this technique is, for example, used in pump probe MOC. So excitation, and then just by stroboscopic technique, you are tracking the position of the vector. In case of ferromagnetic resonance, you're applying RF field with the same frequency. This RF field helps to continue precession, and in experiment, we are detecting this absorption of technique. So I would say it's this process is not a strictly two-level process like this.
Okay, there is one more question from Soyang. I think, why does the line width FMR derivative spectra increase with frequency? What is the physical interpretation of this observation?
Okay. So, well, the classic, well, I would say that we already, each material possesses such an internal property as internal damping or Gilbert damping. And in fact, the simplest theory showed that this damping parameter is part of the line width. And in case, for example, if we have a material with almost non-existent damping or very low damping, like yttrium iron garnet, you almost will not notice the increase of the line width. However, in case of metallic materials, this damping is quite significant, and that's why you see the increase of the line width. And by measuring this increase, you can extract this Gilbert damping parameter with very high precision. Well, perhaps like this.
Okay, thank you. There is one more question, I think from Puspendra. In spin wave mode slide, figure 1, x-axis, field is in Orsted. Is this small field is sufficient to saturate the permalloy?
Well, let's talk. Well, for whatever reason. So which one?
I think in the beginning.
Something slide number 8 or 7, 8, something around that side. Yes.
Somewhere.
Yeah, next, not this one. That slide is.
Okay. Yeah.
Yes.
This is a nice question, because if we'll speak about continuous film, this will not be enough. However, as I mentioned it, in ferromagnetic resonance, shape of the sample plays a role. And instead of continuous film, we have a disk. For disk, this field is enough, because for film, film would be saturated only above 10 kiloersted. Disk would be saturated, I would say, above 7-8 kiloersted of this size. So all these experiments are still in a saturated regime.
Okay. Yeah, please.
It is just, you know, quite a simple formula for demagnetizing factor of disk, and you can see that it will go down for this.
Okay, Puspendra?
Okay, sir. Okay.
All right. I have a very technical question. See, these effects, whatever you are doing, you are making the basically the antenna behind the sample, so to say, lithographically. And you are doing the cavity-based FMR, which is very powerful, but you have a fixed frequency. But you know that this nano-OSC FMR, which is just CPW-based, coplanar waveguide. So this kind of nanostructure with a smaller disk, will it be possible, you think, to measure such spin wave modes using this kind of CPW-based FMR?
Well, no, we were not able actually. Well, with this particular technique we were trying with this nano-OSC system, it still has limitations because in case of, well, if you will, let's say, design a coplanar like ours with just active area of just, I would say 10 micrometers. maybe, and then we'll fabricate disk on top of this and then measure with nano-OSC. Perhaps maybe you still will be able to, because in our case we just mimic our experiments, but still we were using a vector network analyzer technique, and you know that vector network analyzer can also generate at fixed frequency. Here we were using for our experiments fixed frequency for the reason that we can use derivative detection. Derivative detection, as I mentioned, is a very, very powerful tool. If we will just measure in frequency domain, like we are doing with vortex skyrmionic structures, in this case, level of signal would be 100 times lower than in this our experiments that were just specially designed to show that we can detect strong signal from one nano element. In fact, we have measurements at different frequencies. And what we are thinking is also to go into the study of, well, there is a lot of studies what happens with ferromagnetic resonance line with as a function of frequency. Here we want to repeat similar studies for standing spin waves. It also appears to be quite interesting.
Okay, so it's not the nano-OSC, but it is mostly the CPW. Because if you take, let's say, CPW-based geometry, but with a vector network analyzer, so do you think you can still see that or not?
No, but here, once again, all this experiment, well, so sample is, let me. So you see CPV on the one element, and the difference with standard CPV measurements is continuous frequency, field sweeping, modulation of the field. Yeah, that's.
Yeah, I mean, what I wanted to say that the key is basically the microwave antenna.
Yeah.
So it's with CPW based system, it's a bit difficult. Yeah.
Well, but this is CPV. You see, this is microwave, but this is same CPV just with a different design.
Okay.
It is just you see there is a large. Let me see.
Well, but this CPW is very thin, yeah.
Yeah. So, but it is still CPV.
I understand, but I'm talking about why. It's
but basically it means that all of the signal is generated in such a small area.
Yeah.
Because if the line width is thick, so it's not generating a lot of microwave. So all microwave is generated just.
Okay. Thank you. I think there are no more questions. So I would like to request you to stop sharing your screen. I like to share my screen for presenting some small video.
Yeah, please.
Yeah. Okay. So. Do you see my screen? Gleb, okay. Gleb, can you hear me? Puspendra, can you hear me?
Yes, sir, I can hear.
Okay.
Okay, I can. Okay.
All right. Yeah, thank you, Gleb. So on behalf of the W2S team, I like to thank you. So I like to read the small digital memento we like to present you. W2S seminar webinar Synchronix, National Institute of Science Education and Research, NISER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Gleb Kakazei from University of Porto, Portugal. In recognition and I appreciate a very valuable speaker, to give a lecture on spin wave spectroscopy of individual magnetic nanoelements. So thank you very much, Gleb.
Okay.
I really
So
appreciate your time.
Thank
I will
you very
send you
much.
my email, and I hope I will see you again in some future seminars.
Well, let's hope and let's see if maybe there is some kind of Portuguese-Indian collaboration.
Yes, yes, absolutely. And next week we will have Professor Olav Helwig, and I hope all of you can join. So until that, have a nice evening or day, whatever, and please be safe and see you next week. Thank you so much, Gleb.
Okay. Thank you.
Thank you, Wolfgang. Bye bye.
Thank you.
Bye. Have a nice evening. Bye bye.
Bye.